Good evening. So I'm going to talk about temperature, the temperature of the planet Earth, which is at the moment, the average temperature on our planet is 15 degrees. And in the last year, in 2023, it was 1.5 degrees warmer than pre-industrial. And you may know that this 1.5 degrees difference to pre-industrial is also the goal of the part of the Paris Agreement, the United Nations, where the United Nations a couple of years ago decided together that they want to limit global warming to within 1.5 degrees. And we're basically almost there, and someone behind the stage asked me, okay, hopefully there's also a couple of good news tonight, right? But I'll do my best. I'll try. So beyond 1.5 degrees, I'm going to talk about temperature and temperature in the longer time context of the planet. So I'm studying, as the film introduced me, studying paleoclimatology, so climates of the past. And this study really helps us to contextualize this type of temperature differences. 1.5 degree, that doesn't really sound like a lot, but we feel that there's a lot happening in terms of the climate on the planet already. So how does it really compare to what Earth experienced in the past? So I'm trying to give you some information about that. Let's start with that location here. So I don't know if you recognize that. Why is the planet warming currently? It's because fossil emissions, increases in greenhouse gases. I'm sure you're all familiar with that. So how do we know that actually the concentration of greenhouse gas, in particular CO2, in the atmosphere is rising? That's because of measurements, and these measurements are being done in this location. This is the Mauna Loa Observatory, top of a mountain on Hawaii in the middle of the Pacific, the ideal location to monitor CO2 on long time scales, because it's far away from any sort of direct human impact. And a scientist in the 1950s decided, okay, that we should actually monitor this. This would be a really good idea. It's also a beautiful example why scientific infrastructure, big infrastructure, is so important, because you need this commitment to actually do this type of monitoring and these observations on long term. So cutting budgets on these kind of things is a really bad idea, if you ask me. But so you can get the data from the location on the web. Scripps Oceanography Institute has a really nice website where you can sort of watch live how CO2 is rising. So this is the data from the last year. So basically I took this just a couple of days ago. So this is from 1st November 24 to 23 on the left. And this is what happened in terms of CO2 concentration in the atmosphere. So we have something like 420, 425 ppm. That's parts per million. That's not a unit you're probably working with every day. It's sort of not a lot. In absolute terms, ppm, parts per million, that's so 400 is 0.04%. And you see, okay, it actually went down a little bit. You think, like, oh, maybe this is good news, right? CO2 is actually, the last couple of months it went down, but unfortunately not. This is happening every year. This is the seasonal cycle in CO2. And this is related to the amount of vegetation on the northern hemisphere that picks up a lot of CO2 every year in summer. And then when that vegetation decays again over the winter and spring, the CO2 comes back into the atmosphere. So what does that record look like, the whole record, when we look at it? So this is since 1958. This is the entire time series, and you see it has been going up quite a lot, 320 to 425 in this time period. Pretty constant, getting slightly steeper every year. And I've put here some important events. So 1990, Kyoto Protocol, basically one of the first big climate summits, where the United Nations already said, okay, we really need to do something about this. We probably should limit the emissions of CO2. And you see the impact, right? Sort of, if you look close, you can see it. 2015 Paris Agreement. That was really celebrated as a big breakthrough, and it was a big breakthrough, because for the first time there was really, on paper at least, this goal, okay, we really have to limit our emissions to stay within 1.5 degrees, and this is what happened afterwards. Right. And this is, what is this, 2020? Does anyone has any remote memory of 2020? Well, I don't know, it's kind of a gap for me, but this is coronavirus. Indeed, you remember that? When no one was flying, there's someone remember it backstage. No one was flying, we all worked at home. There were less emissions, yeah, we reduced emissions actually that year by 7%, but then we quickly went up again. So also that, not a big impact on the absolute concentration of CO2. So it kind of demonstrates, even with all these measures, these ideas, it's really hard for us to kind of bend that curve around, apparently. Now why, so very quick summary, why does that actually warm the planet? Now, if you want to know why the planet actually has an average temperature of 15 degrees, you need to know three numbers, basically. There's three ingredients. You can make a very simple climate model. The climate models need the most complex supercomputers if you really want to model all the details of it. But if you just want the average temperature of the planet, you need only three things. One, that's here on the left, the sun, incoming radiation. You know how much that is. That's fairly constant, at least for the timescales that we are interested in here. So there's shortwave radiation coming from the sun. We know how much that is. The Earth is absorbing that, is warming up, sends out long-wave radiation until the two are in balance. Now, some of that radiation from the sun is directly reflected back into space. This is what we call the albedo. It's basically the amount that is directly reflected without being absorbed. That's currently around 30%. And if we had no atmosphere, and these were the only two factors, the average temperature on the planet would be not 15 degrees as it is now, but minus 18 degrees. So the difference between the two is because of atmospheric greenhouse gases, and here's one of them, at least one molecule. This is a CO2 molecule. That's a very efficient greenhouse gas. These greenhouse gases cause this long-wave radiation that is coming off the Earth, that this radiation is partially absorbed, actually quite efficiently, and cause the Earth to warm by an additional more than 30 degrees at the moment. And the more greenhouse gases we have in the atmosphere, the warmer the planet gets. So actually we need a certain amount of these greenhouse gases, otherwise the planet wouldn't be habitable. We would basically live on an icy planet. So this is what happened in terms of temperature because of that increase in atmospheric greenhouse gases. So the CO2 record goes back to 1958. This is here the entire period for which we have direct temperature measurements. So we're coming there, pre-industrial, this is our baseline, 1850 to 1900, and then it starts to increase with the Industrial Revolution and the input of atmospheric CO2 into our atmosphere. There's a little bit more variability because there's a few other factors, but by and large, the biggest reason, or the most important reason for that increase in temperature is that increase in anthropogenic greenhouse gas emissions. And you see 2023 here, almost 1.6 degrees warmer. So we didn't really reach that 1.5 goal that we want to avoid yet, because for that you're looking at the long-term average of several years. But I think we can sort of accept that we will reach this in a couple of years. So how does that actually compare to the past? the CO2 concentrations themselves, this increase, how extreme is that actually when we look at the history of the planet, but also those temperatures, how extreme are they? Oh yeah, and this is actually, again, this kind of data is not just, you can't just go out in your garden and just measure and then you get the average temperature of the planet. You need a lot of data points, large coverage, and this is just one data set with all the temperature that goes in here every year and all the time on the oceans. There's other data sets that measure temperatures on land, so there's actually, in this whole time series here, there's millions of data points, right? Right, one of the issues with this very simple model that I introduced here, or a model with these three ingredients, is that the middle part here, the albedo, is actually also influenced by the temperature. So how does that work? So imagine you increase atmospheric CO2 in the atmosphere, temperature rises, then, for example, sea ice and ice sheets will melt. They are very white surfaces that reflect a lot of light. And when this stuff goes, the albedo goes down, so the temperature will go up even more. So this is what we call a feedback process. Right? So some components of the Earth system actually react on the others and can either, if it's a positive feedback, further increase that first change, or if it's a negative feedback, actually reduce the temperature change. And this kind of reaction of the Earth system, the feedback processes, that has, depending on the process that we're looking at, different timescales. So what does that mean? That means when we increase now very rapidly CO2 in the atmosphere, temperature goes up, and even if we would keep then at some point the atmospheric CO2 concentration constant, it could, or what we expect is going to happen, that some of these feedback processes, for example, the melting of ice sheets, actually continues. The whole system has to equilibrate basically to these new concentrations. And that is a big uncertainty. How fast does that go, and how big is the warming eventually with a certain amount of CO2 change? So a doubling, the warming that's associated with the doubling of CO2, that's what we call Earth system sensitivity, when it includes all the feedback processes. So if we only look at the last 100 years or 50 years, that's really difficult to estimate because potentially long timescales are involved here. So we want to look back at the past when climate has changed because of natural causes, and then we get an understanding of what is eventually happening when we increase these greenhouse gas emissions by a certain amount. So let's go back into the icehouse period. So if we want to, for example, know what the CO2 concentrations were before 1958, when John Keeling started his measurements on Hawaii, we need to go to so-called natural archives, natural climate archives. And one very famous one are these ice cores from Antarctica. So Antarctica is a big ice sheet. It's several kilometers thick. And when you start to drill into that ice sheet, you get to older and older ice. Basically, snow falls on top of Antarctica, right? Becomes ice, and that gets sort of buried with time. And when you drill into the deepest parts of Antarctica, you actually get ice that's almost 1 million years old. So that's a nice archive for atmospheric CO2, because when you cut these ice cores actually into pieces, you put them against the light, you see all these little air bubbles in there. So when the snow turns into ice, it actually conserves the past atmosphere in those air bubbles. And what we can do then, we retrieve those ice cores, cut them in pieces, melt the ice, get the air out of the bubbles, and measure the CO2 concentration in there. And that tells us what the CO2 concentration was 5,000 years ago, 100,000 years ago, 800,000 years ago. So it gives us a little bit of a perspective how big that change in CO2 is over the last 50 years compared to what it was a million years ago. So these are the last 10,000 years. So this is Keeling's measurement, or the Hawaii measurements. It's almost now getting a vertical line because we stretch the time scale here. And from here on, we have ice core records. So this is Industrial Revolution starting around 1850. And before that, the last 10,000 years, there was basically nothing happening. Right? It's a flat line. And that means basically, the people in Egypt that started to build pyramids, Jesus, your great-grandparents, the entire history of human society experienced basically the same CO2 values, except so we can feel special, over the last 100 years or so. That also means when we want to understand what sort of the natural system is doing to this, increase in CO2, the last 10,000 years don't really help us any further. We can't really study what the climate is doing when CO2 increases or decreases when we just look at the last 10,000 years. So we need to look further down. I said the ice core reaches almost back to 1 million years. So this is what the last 800,000 years look like. That is getting steeper and steeper. And now you realize already how special these values are in the context of the last almost 1 million years. This is where we are now. This is the last 800,000 years. It never has been even close, atmospheric CO2 concentrations, to what we have here in the last 800,000 years. Our species, Homo sapiens, modern humans, they occurred somewhere around here 200,000 years ago. So we're actually used to relatively low CO2 values. What you do now, however, recognize, compared to the last 10,000 years, there is actually quite some variability. And you maybe see some cyclicity in here, so every roughly 100,000 years, these cycles get a bit shorter in the beginning. There's this change from low CO2 concentrations, something like 180, going up to 280, what we had pre-industrial, and then it's going down again. And I'm not going into the details here, but these cycles have something to do with the Earth orbital parameters. So that's the tilt of the Earth axis and the shape of the orbit around the Sun and the orientation of the axis. These change in cycles through time. That's related to the gravitational interaction with the other planets. And they also lead to a redistribution of sunlight between seasons and latitudes over time. It's complicated, but these kind of cycles introduce then also changes in how the ocean functions. And what is happening every 100,000 years, the deep ocean actually stores more CO2, and then every 100,000 years, it actually breathes CO2 out again. So it's like a deep breath of the ocean every 100,000 years, breathing out again every 100,000. It's like what I did Wednesday morning when I heard about the election. Sort of breathe in, breathe out. This is what the ocean does every 100,000 years. 100 ppm. So this is quite a change, actually. It's not quite as much in amplitude as what we've done in the last 50 years. These changes also take, it looks pretty steep, but it still takes a couple of thousand years. So what did the planet actually look like when CO2 was much lower than these pre-industrial values? When we go down to something like 180 ppm? Was it a different planet because of that? Yeah, it was completely different. The northern hemisphere was, to a large part, completely covered in ice. So this is the ice cover 20,000 years ago. Can I go back? So this is here, when CO2 was down there. This was the ice extent. This is in the middle of what we call the last glacial maximum. Scandinavia was also covered in ice. Canada completely covered in ice. Large parts of the British Isles. And not during the last ice age, but the previous one, so around 150,000 years ago, the ice actually reached also the Netherlands. Right? And you still see some of these remnant sort of consequences of the ice sheet, and that's here the Utrechtse Heuvelrug and the Veluwe. So these little tiny topographic heights that we have, they are actually moraines, terminal moraines of the old ice sheets that reached all the way to the Netherlands. So a moraine, so this is an example, a modern example. It looked a bit different. This is in Alaska, just to give you the idea. So this is a glacier, a small glacier, and at the end of this glacier you have this moraine. So that's the sediment that the ice pushes forward. And when the ice melts, it leaves that sediment. So this is sort of the Utrechtse Heuvelrug in a slightly different size. And to give you an idea, so it was a very. In fact, there was so much ice on the northern hemisphere that sea level was 120 meters lower. You could walk from here to Scotland, and you wouldn't cross the water because you could just 120 meters lower. It was twice the size of modern Antarctica. That is how much colder it was. But what is it actually in temperature? So how much colder does it need to be to actually create an ice sheet on the northern hemisphere that's twice the size of Antarctica? So for that, we also have methods to reconstruct this. We can get some information from the ice cores in terms of temperature, but we want to have the global, the global temperature, right? And for that, we actually do something similar to the ice coring, but instead we go out onto the oceans with those drill ships. This is the JOIDES Resolution. This has been drilling sediment cores for the last 30 years or so. Unfortunately, it had its last expedition last year. But this has collected sediment cores all over the oceans. And similar to the ice cores, so the ocean basins, they actually collect all the stuff, the dust, the sediments that are getting into the oceans. Then those particles sink to the sea floor and accumulate very slowly. And when you drill into the sea floor, you get these kind of layered sedimentary archives. And you start basically at time zero on the sea floor, and the deeper you go, the further you can go back in time. So what do we find in those sediments at the sea floor? As I said, there could be dust, it could be around the coast sediments that come in through rivers, but it's also a lot of tiny organisms that actually float everywhere in the oceans. So like these sea snails, that build these little tiny calcite tests. When they die, they sink to the sea floor, and we find them back in the sediments. So my personal favorite little organism that I study a lot are those foraminifera. They come in different sizes and different shapes. They are actually a lot smaller than this. This is sort of the real kind of scale. They're like little sand grains. They have been around on the planet for a long time. You find them everywhere in the ocean, so they're ideal targets to actually study. And the nice thing is that what we can do is we use the chemical fingerprints in these calcium carbonate tests that are preserved in the sediments. And these chemical fingerprints tell us something about the past temperature, the past salinity, past pH, which is related to atmospheric CO2. So we can use them as an archive for past climates. So what I do personally is kind of my tool. I look at how isotopes are ordered in those calcium carbonate tests. And the amount of ordering of these isotopes tells me something about the temperature conditions under which these foraminifera formed. And therefore, they tell me something about the past sea surface temperatures. You could apply that also to other archives. So calcium carbonate is a mineral that is occurring in lots of biogenic archives. So you could apply it, for example, to seashells, oysters. In fact, you could also apply it to chicken eggs. It's also calcium carbonate. If you have a chicken and you have an egg, you can bring it to our lab. I will measure the isotope ordering in the shells, and it will tell me something about the body temperature of your chicken. Because that's where the egg. It's a very complicated way to determine the body temperature of the chicken. There would be easier ways to do that somehow. But anyway, so this is what I use it for. I use it to reconstruct the past temperature. And there's many other methods. And if you want to get a good picture of past temperatures, you combine these methods, and then you gain confidence in your reconstructions when they all sort of start to fit together. So coming back to our question, so the last glacial period, 20,000 years ago, when we had this massive ice sheet, how much colder was that actually than present? What do you think? Think about it. What do you think? How much colder does it have to be to create such a huge ice sheet that's reaching all the way to here? This is the answer to it. So this is now the temperature for the last 20,000 years, according to our reconstructions. The scale changes here a bit in time, so don't get confused of that. But so these were the last 10,000 years. You remember what CO2 did in the last 10,000 years? Absolutely nothing, right? And temperature does absolutely nothing. This is here what temperature does in the last 150 years or so. This is our anthropogenic warming. And this is what happened when we increased CO2, nature, not we, increased the ocean breathing out, basically, increasing atmospheric CO2 by 100 ppm. Temperature rose by something like 6 degrees. So 6 degrees cooling creates a massive ice sheet on the northern hemisphere. Now, the question is, why did 100 ppm do so much more in terms of temperature there than here? So one of the reasons is that albedo feedback factor, right? When you start to warm the planet by increasing CO2, putting in CO2 in the atmosphere, this huge ice sheet that was present there 20,000 years ago started to melt. Less light was reflected out into space. So we had a positive feedback. There was even more warming. And this can explain this very large warming. And one of the questions is now, of course, what actually happens when the whole system Earth equilibrates to these 430 or maybe in the future 500 ppm? How much more warming will we actually get in the long term? So apparently when we look at the last 800,000 years, CO2 was never higher than now. But the history of the Earth, of course, is a lot longer than only 800,000 years. So what happens when we... Oh, there's my cocktail. Excellent. Cheers. Cheers. I ordered that. It's feet long timescales. I ordered that an hour ago. The history of the Earth, right. So it's a lot longer than 800,000 years. How old is Earth actually? Pretty old. It's 4,500 something million years old. And well, we can sort of forget about the first few 100 million years. A pretty wild planet. We don't know much about it. There's not much left of it. Somewhere here, Earth, for some reasons, life appeared. But actually only the last few 100 million years are sort of well preserved, and we start to actually have a good fossil record for these time periods. So we could look at the last 500 million years and try to reconstruct what climate did over those time periods. Maybe for your reference, here that's the Mesozoic, that's the time period of the dinosaurs. They ended here at the Cretaceous Paleogene boundary when a big meteorite hit the Earth and wiped out the dinosaurs around 66 million years ago. Then we had here the Cenozoic, that's the last 66 million years ago. There we actually have quite a good image of what the Earth and the climate looked like. Before here it's getting a bit more difficult, a lot more uncertain. And the last 800,000 years, that's somewhere up there. Only the very last bit. Humans appeared even later, not really visible. So we can also study those older periods. We can go back to our oceans, again, look at those sediment cores, but when we look at older time periods, we also have to look at rocks that are actually on land, because most of the old, let's say the older crusts in the oceans that actually disappeared due to plate tectonics. But when we go on land, we find here and there also for these very old periods, rocks and sediment sequences that we can study to reconstruct past climate change. So this is what we do with, for example, also here, this is with some students, where we study these types of sediments in Spain every year as part of their education field work. So here we actually see sediments from the Cretaceous here on the right in these red colors, and on the left sediments from this Paleogene. So also these sediments were at some point deposited on an ancient ocean, and then through mountain building processes in the Pyrenees, all of these sediments were actually tilted up, and you can walk along the coast there, somewhere between Bilbao and San Sebastian, and actually walk through time. Right? So you walk here through the Cretaceous, every step is something like 20,000 years, and then you come to this layer, and that is actually equivalent to that's the very moment when that meteorite has hit Earth, and the dinosaurs were wiped out, and then we go here into these, into the Paleogene. So we can study these kind of sequences all over the planet, and we have different methods to reconstruct also from these sediments CO2 concentration. So what did CO2 actually look like for the entire period, the entire last 400 million years? And this is what it looked like. So I have to go slowly through this. There's a lot of information here. Time scales, again, is sort of changes logarithmically. So the further you go to the left, the more time is in the same amount of space. So we are now here, right? 420 ppm at 2024 AD. This is the change in CO2 that we've seen over the last 150 years. This was the boring, let's say, last 10,000 years where nothing was happening. This was our ice core record, the last 800,000 years. Every now and then, well, every 100,000 years, CO2 went down and went up again to those pre-industrial values. And then we go into what we slowly can call deep time, right? So now we are making jumps here millions of years back in time, and we see that when we want to reach the values that we have right now in the atmosphere, we have to go back something like 3, 4, 5 million years into the Pliocene. Then we have similar values. If we then go further back, something like 50 million years, we see already CO2 was a lot higher. It was going towards 1,000, maybe even up to 2,000 ppm. And then when we look at the few 100 million years before that, we see that it almost all the time had much higher values than we see now. So what does that actually mean? now, it means that we live in a period that overall, for natural causes, has pretty low CO2 values in the atmosphere, right? There was this period here somewhere in the Carboniferous where it was sort of similar to what it's now, but overall, most of the history of the Earth has seen higher CO2 values. And you may ask yourself now, where is all that CO2 coming from and what is causing those changes? I mean, there were no humans around, we don't think. So where's all that CO2 coming from and where did it go? And this time it's not the ocean breathing in and breathing out. This time it's actually Earth, solid Earth itself. So these long-term, large changes in atmospheric CO2 concentration are related to two things. Volcanism, so periods of strong volcanism lead to high concentrations in atmospheric CO2. And the breathing in is basically the storage of carbon in the crust, in rock depositions like coals, oil, but also these kind of carbonate deposits. And this is happening typically on very long timescales, millions of years. So over the last 50 million years or so, there was a tendency of, let's say, store more and more carbon into the crust of the Earth. And we are partially now, or actually to a large extent, getting it out again by burning fossil fuels. So what did temperature look like then? If CO2 was so much higher in the past, and we think that CO2 is causing warming, was Earth actually a lot warmer back in these times? And this is the latest reconstruction for this entire period of 485 million years. So to orient you, we are now here, 15 degrees, average temperature of the planet. It's a very long time scale now. During those ice ages, temperatures cooled by several degrees. But then when we go back further in time, actually most of Earth history, at least the last 500 million years, it was almost all the time warmer than it is now. And during these very high CO2 periods, for example, here in the Eocene, but also further down in the Cretaceous, average global temperatures went up to 30, maybe even 35 degrees. So that's 20 degrees more than what we have now. And did the planet look different? Of course, when you have these temperatures, the planet also looks completely different. So the Baffin Bay in Canada, a place that is mostly covered in ice most of the year now, was back then, for example, in the Eocene 50 million years ago, was a swamp. We find crocodile fossils in those high latitude areas from these hothouse periods. We find palm tree pollen. It looks very different. Obviously, there was also no ice sheets. It was much too warm for any ice sheets. And sea levels were therefore also a lot higher. And for example, if you think about what would happen if we melt all the ice sheets that are present on the planet right now, Greenland, Antarctica, Greenland is 7 meters sea level, Antarctica something like 63, so we're talking about 70 meters sea level rise when we melt all of that. So obviously in these past periods, the continents were also in slightly different locations, but when you rise the sea level by 70 meters, you can imagine that a lot of places that are now dry would then be covered in water. Now, aside from those temperature changes, CO2 changes, we can also look at other things in those sediments. And this is also actually from the field work that we do with second-year earth science students. So this is also in Spain, south of the Pyrenees. And it was an incredible hot day when I took this picture. It was something like 40 degrees, not a great condition to do field work. but it kind of fitted the kind of sediments that we were looking at. So this is also in the Eocene, a period, one of these past periods that is very, very warm. And in this period, you had sometimes these so-called hyperthermals. So one of the biggest ones is actually at the start of the Eocene. And that was also back then related, 55 million years ago, to a relatively short period of extreme volcanism. And temperatures rose by something like 5 or 6 degrees globally. And so these sediments here, those red sediments that you see there, that were uplifted later, now are accessible because of the sort of Pyrenees mountain building. They were originally deposited in an sort of, you can imagine a flat fluvial plain, sort of meandering river systems with plains around it that are occasionally getting flooded. And then you see all these very fine-grained red clays being deposited there. And at the time when temperature actually suddenly rose by several degrees, we have a layer up here in this section that is preserved from this period. Suddenly the sediments become completely different. There's actually up here a layer that spans several tens of kilometers of these very coarse-grained conglomerates. So this nice fluvial plain suddenly turned into some kind of extreme river with a lot of discharge of water. And it's something that you would expect when the temperature suddenly rises by several degrees. Because for every degree Celsius that Earth atmospheric temperature rises, the amount of water vapor in the atmosphere can increase by about 7%, according to thermodynamics. Right, so when it's getting hotter, the atmosphere can carry more water. And when the atmosphere has more water and warm, wet, atmospheric parcels hit sometimes cooler air, then all that water comes out suddenly, and then you get these huge streams in those floodplains there. And since it was in Spain, it kind of reminds you what happened in Spain a couple of days ago, right? A couple of weeks ago. So it's not a conglomerate, it's not a rock with relatively large pebbles, but it's a kind of human conglomerate. And this is something that you expect from the rock record. When it's getting very hot, the hydrologic cycle changes, stronger rainfall events, and this is also what we're seeing here. Now, if we now take all the data together for the last 500 million years, all the CO2 data and all the temperature data, can we find some kind of relationship between temperature and CO2 doubling? And if there is such a relationship, would that maybe help us to predict what is going to happen eventually once the Earth has equilibrated to these high CO2 values? So this is what that data looks like. So we have here on the lower axis atmospheric CO2, logarithmic scale, and here we have global mean temperature. So in green we have the last 60 million years, so it's putting now this temperature record and that CO2 record together and plotting it next to each other. And when we go further back in time, those Mesozoic, Paleozoic, so that's more than 60 million years ago, so the data becomes more uncertain, there's larger error bars, but overall there is a relatively solid picture, especially if you consider the more certain values over the last 60 million years, the green dots, that tells us, okay, with every doubling of CO2, we get a sort of constant shift in global mean surface temperature. And the slope of that line here, of that black line, is this relationship. So with every doubling of CO2 over the last 500 million years, on average, the planet warmed by 7.5 degrees. So what does that mean for us? So this was where we were pre-industrial, 13.5 degrees, 280 ppm. And this is where we are now. 400 something, 25 ppm, 15 degrees. And CO2 is growing, so we are shifting slowly towards the right. And what the paleo record suggests, right, but it's still a big question where a lot of research goes into, so how quick does that go? But what this record suggests is that once the entire Earth system actually equilibrates to these new CO2 conditions, you would actually expect that this point is moving up towards this black line. Right? So, and if we would go to a doubling of CO2, so that would be something like 560 ppm, with a current rate of increase, something like 3-4 ppm every year. We reach that in 60, 70 years. And then if we wait long enough, and that is the question, how long do we wait? Have to wait. We would expect that the increase in temperature is actually not 1.5 degrees, but it's more going towards 7.7 degrees. Which is a bit of a concern. The important point, however, is that we are not sure what the timescale is of this equilibration. So how long will it actually take for the system to pick up? And that is, of course, timescale is very important if we're thinking about our lives, right? Okay. So this is what we call the Earth system sensitivity, and this is actually one of the major points, I guess, of sort of take-home messages, that when we look at the past, the increase in temperature with a certain amount of CO2 or doubling of CO2 is actually a lot higher than what we've seen so far in the last 50 to 60 years. So this paleoclimate data would suggest that we should see a lot more warming, even if we are stabilizing at some point at a certain CO2 level. I said it already, speed matters. And thinking now about the person who asked me to come with some bad news, good news, sorry. I'm in doubt if I should show the next slide, but I will never, because I try to make it into good news. So this is my last example of these past climates. Now, when we're thinking about these past Earth periods, even when temperatures were really high, there was a rich fossil record. There was a lot of biodiversity. So apparently, if you do the change over long time scales, and I'm talking about thousands to millions of years, evolution can actually pick up, and organisms, so the biosphere can actually learn how to cope with it. Right? This is also what we learn from the paleo record. However, there were a few periods in the past where the changes were extremely rapid. And then we get these extreme mass extinctions. So one example I talked already about was this big meteorite that basically wiped off the dinosaurs. Another example is here the Permian-Triassic boundary. A couple of 100 million years ago, it was the biggest mass extinction event that the Earth has ever seen. More than 90% of all the organisms died, and the reason was a relatively short period of extreme volcanism in what is today Siberia. So atmospheric CO2 increased in a relatively short time, a few thousand years, from something like 400 to 2,000 ppm. And if you compare the modern change in atmospheric CO2 to what happened there in terms of its rate, we are totally dwarfing this, right? It's going so much faster than what we've seen or what Earth has experienced there. So this is another reason for concern. So it's not only in terms of amplitude at some point getting very large and uncomfortably hot, but it's also getting really fast. And the sort of hope, however, is that this was a super volcano, basically, right? If this would happen now, we are toast. We couldn't do anything, right? It's like a meteorite. However, compared to this, we are now, at the moment, we are increasing CO2. And we basically know how to stop it, right? We actually, it's not a scientific problem in that sense. We will at some point have to actually suck CO2 out also of the atmosphere. That's a bit of a scientific problem, but I am confident that we have at some point the tools to do something about it and reduce our emissions, but we also really have to do it. And with that, I would like to thank you for the attention and flush it down with a few cocktails. So, thank you.
They say that it's something funny, relaxing somehow, trying to find new words to speak. Everything is twisted, but they got something unique.